focus on the discovery of the radio mission. First, I want to just talk, what you might expect for radio emission from a neutron-star merger. There's actually a whole list of components you can expect. Very speculative component is you might get a low frequency pulse of radio emission due to things like the interaction of the magnetospheres of two neutron stars close prior and during merger. Of course, the jet ISM shock, the possibility of magnetar formation along with magnetar. We've already heard a little bit about the interaction of the jet with the projectile, giving you a cocoon. And then, of course, the most reliable one is that you will have some few percent of the solar mass potentially ejected interacting with the ISM. So, to the best of my knowledge, there's no observations that constrain whether or not there's a low frequency pulse, although I want to discuss it a little bit later on. And similarly, if there was a long-lived magnetar with energy being dumped into a clarion, we would have seen a huge radio afterglow, and that's not the case. So my focus will be on these three components, and I'm actually taking stills from a lovely video from NASA, and then completely changing the interpretation. Apologies to Brad, just for the sake of having the illustration. Of course, with the dynamical ejector, you've got some, a few percent of the solar mass being ejected. It's traveling outwards at 0.2c or something like that, and it's basically sweeping up some mass, and at some time you see a rise of a radio afterglow on timescales of months to years. Both the luminosity and the timescale are very sensitive to the energy in the ejecta and the surrounding ISM density. In the case of a relativistic jet, you expect timescales that are much shorter, which are days to weeks, and in this case it's very sensitive also to the orientation of your line of sight to the jet. If looking down the barrel of the jet, you'll have a much brighter afterglow on shorter timescales. And the third option is this possible interaction of the jet with the dynamical ejecta, either tidal or wind-driven. And there are two possibilities here. One, that jet dumps all its energy into that cocoon, and that eventually breaks out. You get a very bright radio afterglow associated with that cocoon breakout. And the second possibility is that the jet actually dumps only some of its energy into the ejecta, still breaks through, and in some universe, someone still sees a classical short gamma ray burst. We see timescales of days to weeks, months to years, weeks to months. I can't really go along to the VLA and say, give me the telescope every day for the next year or so. We have to have some better constraints, and happily in the era of multi-messenger astronomy, that's the case. We know there was a short gamma ray burst, or burst of gamma rays, depending on your interpretation. 1.7 seconds after the merger, we have a bright optical NIR and ultraviolet afterglow. And as is really nicely described by Raffaella, there was an X-ray after that pops up after 9 days. And in fact, there's also more recently been infrared Spitzer detection. And for the radio, this is really important for reasons that have been touched on by Raffaella. The popping up of an X-ray after 9 days is consistent with actually both the alpha-axis jet model and also the cocoon model. So at that point, we were taking the possible range of power laws you might expect. We were very excited about seeing the radio afterglow very soon after that. So we engaged our array of instruments that were lined up. This includes the very large array in New Mexico, which is still the largest and most sensitive interferometer at gigahertz frequencies. We had the GMRT, the Giant Meter Wave Radio Telescope in India, and the compact array in Australia. And we pretty much observed on an almost daily basis with most of these instruments in the days following the detection of the X-ray afterglow. Here is an image that showed up on my screen after about 48 hours with not much sleep. Here's an optical image from Kaziwala et al. 2017, which shows the Gemini image comparison. As has already been discussed, there's a bright radio source at the nucleus due to this low luminosity AGN. There's a couple of background sources, and this little smudge here. Initially, I thought I'd sneeze from the screen. I was very tired, but we did some analysis on with the next day's data, and that eventually ended up being our afterglow. And in fact, when you watch that evolve over the following 2 weeks, you can clearly see it getting brighter. And that's what we're going to use now to try and constrain the various components of the jet we might be seeing. Before that, I want to also mention that we did some orthogonal investigations into what the ISM density might be at the location of the merger by looking for H1 and trying to constrain what the fraction of neutral hydrogen was, and therefore infer what the local ISM density was. And based on the non-detection, here is our radio velocity in our observations. This was an hour of observations with the Green Bank telescope. Here's the NGC 4993 radio velocity, and here's the parameter space we searched for a signal. With no detection, we implied an upper limit on the neutron mass hydrogen mass rather, about 10 to the 8, and then with some conservative constraints on the geometry, we assume a implied local density of less than 0.04 per centimeter cubed for the ISM density. So that was a good independent way to constrain what we might expect to see in the radio. For modeling, we worked with Audrey Clark and Holger Zaka and Steve Paran, using models described in Soderberg et al., but they're also consistent with box fit, and in all cases we used these same parameters, and we tried to constrain our data to be consistent with X-ray data, as described in Raphael's talk. Okay, what did we learn? First thing I want to touch on is this question of a classical short GRB. In this case, I'm referring to the low luminosity GRB that was seen, and whether that's consistent with someone somewhere in the universe seeing a classical short GRB in the typical range for the population observed by Swift and Fermi et al. I think there's been a lot of discussion already about whether it's on axis, and there's very little evidence to support that. I want to add to that the discussion in Kaziwala et al., which argue that such a low luminosity on-axis jet would actually have trouble breaking through. But what we actually constrain from the radio data is that it's very unlikely that the radio emission, from the radio emission, that we're seeing this a classical short GRB slightly off-axis, i.e. that we're just seeing the edge of the jet, and that's the reason why it's so low luminosity. Because if it was, we would have seen a very bright radio afterglow. I'm going to show you 3 examples, and all we're varying here is density. Here's our radio light curve. Here's the density of about 10 to the minus 3 electrons per centimeter cubed. Here's 10 to the minus 5. And to get a fit to the data, we had to assume a density of the ISM of 6 by 10 to the power minus 7 per centimeter cubed, which is basically more consistent with the IGM than the ISM. Getting back, so of course the other option then is that you're looking at something that's widely off-axis, and that's the debate now, whether you're seeing a classical short GRB off-axis, or whether GRBs can be explained by something else, for example, like a cocoon. And there are arguments, for example, in Gottlieb et al. It was a really nice paper that discusses how the gamma rays can be produced in the cocoon model, and they also argue that it's very difficult to explain it as a classical GRB seen off-axis. But I'm not going to debate that. All I will say is that with radio observations over the next few months into the next year, we should be able to constrain that. So getting back to this picture of our 3 types of projecta, what are we seeing? I think with data thus far, and once again we're only still in the early days of radio observations, I think it's unlikely we're seeing the dynamic projecta. There is a model fit that we do get, assuming that you're seeing the very high velocity tail of the distribution. And the implied velocity to reduce the radio emission we're seeing is 0.7 c for that tail, which we deem unlikely but possible.
How much mass is it? That point, do you remember?
That's taking the mass of the from the optical, and then
I see. So the whole mass. Okay, for the whole mass.
And then just taking the tail, putting a power on, and then just taking the tail and saying, how much mass? Not much mass to give you, but it's traveling so it's traveling so fast. It's almost manualistic at that point. And for the 2 other options. We find that the light curves are still consistent with either a relativistic jet observed off-axis or this cocoon model. And here is our data as shown in the paper, looking at these 3 possibilities. We have the strong cocoon model, a weak cocoon model, and an off-axis jet. I should mention that there's a range of parameter space for the off-axis jet that fit the data, because you can trade off the ISM density and the isotropic jet energy to give you a range of fits. And I should also point out that actually the data are generally consistent with the density of between 10 to the minus 3 and 10 to the minus 2 electrons per centimeter cubed. So of course over the next few months we will get more data to try and constrain this. I want to point out an additional model that was produced after we were already past the stage where we put it in the paper, but it is included in Gottlieb et al. And that's once again looking at the strong cocoon model, and they actually tried to produce a model that fit all the data, including the gamma rays, X-rays, the blue optical, and the radio. And this is their fit to the radio data with this model, it gives a pretty good fit, but it predicts actually a continued rise over the next couple of months, which we can add to our 3 other models. So constraints in the spectrum, it's already been mentioned that you expect essentially a fairly flat spectrum to be able to relate the X-ray and radio, and what we're showing here is just that exact model is broadly consistent with the data. The data are not very constrained thus far, but we've been doing further observations that are much more sensitive, that we should be able to get a direct measure from the radio across a wider frequency range to constrain what we measure as the radio band spectral index, and compare that to what we saw for the X-ray in the coming weeks. And what I think is also really exciting, we have an entirely orthogonal way to actually try to constrain models here. And that's just based on the expected angular diameter of the fireball as a function of time for the various models. Because you expect for an off-axis jet that it would be basically broadly larger at this stage than, for example, a cocoon, and of course much larger than something that was traveling at a subrelativistic velocity. And in later times you may be able to resolve between a choke jet and jet breakout. But I think the main thing we wanted to resolve between is to be able to distinguish between the off-axis jet model and the cocoon, and combine that with the light curve to really get a good fit for what we're seeing. A pretty way of looking at that is like this. This is the approximate scale we expect from those previous models of the dynamical ejecta, the jet, and the cocoon, with a little dot to represent our solar system. And the hope is that sometime, what we're doing right now is we're using a technique called VLBI that some of you may be aware of. Involves getting dishes right across the entire continental US and beyond. This is an instrument called the VLBA. It has 10 dishes across the US. It's not sensitive enough. So what we've actually done is we've brought in the Green Bank telescope, the largest single dish on the planet, and we've brought in all the 27 dishes of the VLA. Combined, you've got a 38 dish array that is the most sensitive, most high-resolution radio instrument on the planet. And I'm hoping, we've been doing observations over the last month or so, and for the next 2 months, I'm hoping soon we get the first nice snapshot of the afterglow of a neutron star merger. Of course, it'll look more like this. It'll be a blob on the screen, but it will be a blob you can fit a Gaussian to and determine whether or not it's resolved, depending on your signal to noise. And that will allow you to measure the front velocity of the ejecta, and hopefully then break the genetics between these various models. One last thing I want to talk about that's unrelated to this event is the exciting, I think it's a potentially exciting possibility, is looking for this low frequency radio pulse in the future. And I think it's exciting, even though it's pixie dust. It might not exist. It's poorly constrained, but in some models it's actually even a precursor due to interactions of endospheres prior to the merger. The idea of having a low frequency radio burst before the merger, to me, is so exciting that it's worth at least investigating. And we have a new array that my group has built in the Owens Valley in California that operates at very low frequencies where this pulse should happen. It images the entire sky, and I hope it might be a useful tool to constrain whether or not this kind of pulse is present. This is just a quick movie showing this dipole array. You'll find that all these dipole arrays have drone videos because they're not very impressive from the ground. And here's some graduate students for scale. This is just the inner core. And this array is dedicated to imaging the entire sky every 10 seconds, and I hope it'll be useful for this kind of project. Here is, you can't really see it very well, here is the entire sky at radio frequencies in a 10-second snapshot with our array. You get the entire sky, you pay a huge penalty in data rate. You get 30 terabytes of data per day. In raw form, it's 20 petabytes per day. And there's 10,000 sources on the sky per image. And you just watch movies before and after. This is actually a short gamma ray burst data set actually. And about halfway through the burst goes off and we look for this pulse. A neutron star merger is much more exciting, it's much closer. Why didn't we detect it during this recent event? Unfortunately because it was below the horizon. So we see the entire hemisphere, it's only half good enough. And here's actually an image from 12 hours earlier, and here's the location of the localization region. I hope in 03 we get an event that's above the horizon. We can try and constrain precursor and prompt emission.
So maybe you said this, but what was the time delay that you'd expect if it came at these distances?
So you mean just because of the propagation effect?
Yeah.
Very, very small in the case of this particular event because it's only 40 megaparsecs away. And we're seeing it out of the galaxy, and we're also seeing it through very tenuous ISM in its host galaxy, so not very long. For short gamma ray burst, it's quite long, and it's not, the dispersion delay is not destructive. The scattering is much, much worse. If you're scattering broadly, then that's, going to ruin your signal. For this if this event had been above the horizon, it would be fantastic because there would be an effect due to that dispersion and scattering. Okay, so I'll stop there and just leave up my summary. But radio observations are still ongoing, so watch the space. I hope the radio data can be the data that allows us to resolve between models. And at some point in the next year or two, we should see the actual kilonova radio emission rise. And in the future, I hope a prompt burst, maybe even a precursor burst, could be an exciting avenue to explore. Thank you.
Yeah, can you tell me more about this 20 petabyte to 30 terabyte conversion? Do you lose the potential to actually observe events? I'm asking, let me
Sure.
say why. Because I mean, we could give you in principle a gravitational wave, it's somewhere like that if
Right.
it helps to store data.
But yeah, we lose no information there. This is pre-cross correlation.
Okay.
This is what we got to push to our electronics. But our final data product is 30 terabytes.
Okay.
And then there's ways to try and reduce that, but it's there you start losing information. So we kind of leave it as it is.
But I mean, I'm more asking like because if you wanted to make a case for us getting prompt information to you, we could do that if it was helpful. But if it's not, then
It might be helpful because we could, there is one way that it helps. So we run a buffer of our visibility data, and that gives us the so I can, everyone else is usually chasing the short GRB. We just take our time and go back to the buffer and pull it out.
Yeah.
But to have really high time resolution, like a microsecond time resolution, which is really what you want,
Yeah.
then you got to buffer that 20 petabit stream.
Yeah.
And that's where we would really benefit from having a prompt,
So
a prompt trigger.
what's the current buffer that you have sitting there?
24 hours of the visibility data, but no buffer of the really high data stream. So we could run that buffer. We're going to build one in the next year, and we could absolutely run that if we knew there's going to be a prompt trigger.
And what time scale would we need to give it to you on to be useful for that buffer?
I have to do the calculation in terms of how much data, but I'd say minutes would be a few minutes at most. Lunchtime.
I think people are hungry, but let's thank them again. Just so everybody's aware, women's bathrooms are by the elevator on this floor, men's on the next floor. Grab some pizza. We're going to hear, let's take about 15 or 20 minutes to eat and get ready.